Hello, everyone, and a very warm welcome to today's session. I'm Achal Srivastava from the Marcom team at LTSCT, and it's my pleasure to welcome you to the very first session of LTSCT webinar series, which is shaping the next generation semiconductors. This series is designed to bring together leading voices from across the tech ecosystem to explore how semiconductors are shaping the future for energy, mobility, and industrial innovation to intelligent system and sustainable infrastructure. We will begin the session with virtual fireside chat on powering the future of energy with next generation power grid design. Over the next hour, we will explore how advanced materials like silicon carbide, new generation architectures, and embedded design intelligence are coming together to enable the sustainable and future ready energy infrastructure. To guide us through this today's session, we are joined by someone who brings deep insight and vision to the world of semiconductors. It is my privilege to introduce and welcome our moderator for the day, Mr. Sanjay Gupta, who is the Global Head Engineering at L&T Semiconductor Technologies. Sanjay is an accomplished semiconductor leader with over 29 plus years of experience of global across semiconductors, embedded software, and electronic system design. He began his career at Motorola and went on to become the Global Vice President of Engineering and Managing Director for NXP's Technical Innovation Centers. He also holds an MBA from ISB Hyderabad, where he was recognized on the Dean list. Before joining LTSCT, Sanjay led the Advanced Technologies business at Minda Corporation as President and CEO. He has worked closely with government bodies, industry leaders, and academia to strengthen India's semiconductor ecosystem. He has served as chairman of IESA Executive Council and advised the Ministry of Electronics and IT on key political initiatives. A technologist at heart, Sanjay holds multiple US patents and has authored numerous technical and business publications. At LTSCT, he is driving the engineering strategy that powers innovation and national impact. It's a pleasure to welcome you, Sanjay. Let's dive in.
Thank you, Achal, for a very nice introduction indeed. I will try to live up to that in today's session. But more importantly, today's session itself is so insightful, partly because it is going to change the future, and partly because it's my pleasure to introduce my dear colleague, Mr. Andres Carvallo, who is our global head for energy at L&T Semiconductors Technologies. So before we start the session, I would like to introduce Andres for the kind of visionary leader he is. And very aptly, the talk for today's discussion, Powering the Future of Energy, the Next Generation Power Grid Designs. There cannot be a better person than Andres to throw light on this futuristic topic. Andres is an award-winning engineer, author, and executive with a very illustrious career spanning over 36 years across energy, telecom, and computers, software industry. He's recognized by IEEE as a pioneer of the smart grids, and he has been instrumental in shaping the future of intelligent energy systems since 2003. I was very pleased to know that our colleague Andreas has authored more than 40 books on various topics, including energy and grids, which is amazing. He's best known for leading Austin Energy Smart Grid Program, which is one of the most celebrated implementations globally. And he has co-founded Pecan Street Project, which is considered as a trailblazing initiative that redefined energy innovations. Throughout his career, Andres has overseen more than $4 billion in advanced energy products and delivering impact at really global scale. In the private sector, he has held influential leadership roles at companies such as Microsoft, Philips, Hewlett-Packard, Borland, and several high-growth startups, where he brought together technology, vision, and execution. Today at L&T Semiconductors Technologies, Andres leads our global energy portfolio and a business vertical where he's driving strategy, innovation, and the ecosystem partnerships to support smarter and more sustainable energy future. Please join me in welcoming Mr. Andres Carvallo to this conversation.
And hey, thank you.
And I'm sure that
Thank you,
everybody who's
Sanjay.
part of this will really cherish this. Thank you, Andres, for part of being, this chat.
Thank you for having me. Thank you for having me. Can you hear me okay?
Yes, yes, absolutely. You are absolutely audible. Now,
Yeah,
let's get directly into this topic,
sure.
where we will have a very important theme, as we just said. The theme is powering the future of energy, right? And this itself looks so impressive, and within that, how we will be defining and designing the smart next grid power grids for future. And to address this topic, there are different themes that we have designed where we are going to take a deeper dive. Uh, the electric grid, just to set the context, that has been a marvel of 20th century as an innovation which went through unprecedented challenges in last few decades, namely the penetration of renewable energy, the decentralization of energy, and the increased demand volatility, right? And these mega trends are driving some of the unique disruptions that this industry is seeing. And uh, we are going to take a deep dive into, along with semiconductors, both hardware, software, and security, how they are going to innovate and how they are going to disrupt this smart grid transformation with Andreas. In addition to that, we are also at a critical juncture in the evolution of energy at this point everywhere in the world, including India. And the decisions that we are going to make today, they are definitely going to shape the reliability, sustainability, and accessibility of the power for generations to come. And hence, this topic has become more important than ever before. And there's an urgent need for the modernization of our power grids. And that is where we are going to lead our first question to Andreas. And just as a side note, throughout this discussion, if you have questions and queries, we have a Q&A box where you can put your questions. And towards the end of this session, we are going to go through, those questions as well. So without any further ado, let me straight away jump into the discussion point. So, Andreas, as we are getting into this, this topic, the energy landscape is being reshaped by a confluence of very powerful trends, right? And these trends are driven by some of the key drivers, which we would love to hear from you. That what are those drivers and how they are going to shape, this landscape for times to come. Over to you.
Sure. Well, thank you for the question. I'm delighted to be here with you, and looking forward to the questions at the end from the audience. And the key drivers are really, the transformation of what's been happening for a while now. I would call that there are, three big mega trends: digitalization, decentralization, and decarbonization. They're kind of forcing this transformation globally of all industries, and energy happens to maybe be one of the last ones that is jumping into the whole automation and leveraging computers and semiconductors everywhere. But clearly, it's we see it everywhere, or we feel it everywhere. Where it's really the notion that you have in your house, perhaps solar panels and energy storage, and you have smart appliances, and that's beginning to disrupt the grid itself. You're also, perhaps have one electric vehicle or two. Maybe you have a Tesla, um, and obviously, as the Tesla charges, it feels like it's a brand new house while the Tesla is charging for the grid. So when you imagine the best-selling car in America is the Model Y from Tesla, that car is now proliferating in the U.S. in a significant fashion, and globally for that matter. Those vehicles are doubling the size of the edge of the grid when they're charging. And then obviously we hear a lot about artificial intelligence and cryptocurrencies and the next generation data centers. And some people talk about, traditional data centers used to be, um, um, you know, uh, structures that consume or require anywhere from a few hundred megawatts to maybe something like 500 megawatts at a time. And now data centers are being designed to do 1 gigawatt or up to 10 gigawatts. And so the growth and the scale of that edge of the grid infrastructure needed, it's also driving the need for new transformation and innovation. And obviously, you know, manufacturing is going robotics, and which means more electricity. And then you have things at the edge of the grid with called virtual power plants, or the transaction that will take place from me selling my excess capacity on my solar rooftop to my neighbors or my friends or my family members, right? And at the same time, the need for not wanting to be part of an outage in the Department of Defense base for airplanes or the Army or what have you, or maybe I'm a hospital, or maybe I'm a mission critical producer, maybe I'm a food store like a supermarket, and I don't want to be down when the grid is down, so I build my own microgrid with my own generation resources. So all these changes are driving and creating a new need for reliability and interaction, and obviously a big need for cybersecurity.
Great. I think this is definitely a lot of critical drivers that are changing the landscape, and that leads me to my next question about our current grid was built for a simpler time, right? I mean, these things happened in 20th century, and we felt like they are going to change the world forever. But with power flowing in only one direction, because that's how the world was, and as the innovations are happening, what do you think? What are the core limitations we are facing right now, and why a fundamental redesign is necessary? And the complete disruption is the call of the day.
Absolutely. No, and you know the thing to start the thought process is that the grid was created by Edison and Tesla, and it's been around for 135 years. And name one innovation that withstood 135 years without being changed, and that would be the power grid. But the power grid now is finally being challenged by all this trends and disruptions at the edge of the grid that require better management for power quality and harmonic and modulation. And so the grid originally was created as a one-way power flow from the central generation station all the way through the transmission distribution line, whatever is at the edge of the grid. And so this one way of sort of creating, electrons and moving the electrons and balancing the grid at either 50 hertz or 60 hertz is being challenged dramatically. And so as devices proliferate all over the grid, they also bring with them the notion of more points of failure possibilities, the challenge of cybersecurity and being very vulnerable. And so the architecture of the grid recently evolved to what I call a two-way power flow, two-way data flow grid with controls for real-time monitoring and management everywhere. So today the grid is highly controlled from the central power generation through the transmission lines all the way to the substation. But the grid, for the most part, is blind and has very little controls, very, very little automation from the substation through the distribution lines, all the way to your house, the hospital, the office, the school. And so the instrumentation that needs to come to bear is on that side of the grid. Similarly, the generation not only is happening at the central utility scale generation, but now the generation and the energy storage is happening at the edge of the grid. So imagine all the cars at the airport being electric, and all those cars having the ability to send energy back to the grid and integrate and help the grid with the balancing of the 50 hertz or the 60 hertz, depending on the geography. That use case drives a new need for synchronization between what the utility and how the utility manages its own assets to maintain the frequency and balance in the grid versus what's sitting at the edge of the grid interacting with the grid real time dynamically.
Great. So I think that is a very very good perspective on to how this whole thing started 100 200 years back, and how we are being challenged because of the way the ecosystem has changed, but the grids have remained the same, hence the limitations. So that leads to the next question for our audience, and I'm sure that will be really insightful, that if these are the limitations, right, there has to be a solution. So what does that next generation power grid that you have conceived looks like, and what will be the defining characteristics, so that as a ecosystem, various players from semiconductors players, the utility players, the infrastructure players, they all can embrace to this new reality. So the picture that you're painting, if you can get deeper into that, I think that will be awesome.
Sure, absolutely. No, it's really the big thing about it is it's a journey, and it's a journey because infrastructure at the mission critical industrial utility scale side needs to be replaced, but it cannot be replaced quickly for obvious reasons, right? This infrastructure tends to last 20, 30 years. And so it's very difficult for every grid element and every grid operator to, all of a sudden decide, okay, we're building this two-way power flow, two-way data flow grid tomorrow morning, and we're going to swap everything, and we'll go to, electronic store and buy all the devices, and we're done, right? And easier said than done, and it's not that simple. But clearly, what needs to happen is that the grid is shifting from being totally centralized to being decentralized, which means that the grid and the grid operators need a new architecture on how the electrons not only flow one way from the utility central generation units through the transmission and distribution wires, but how they also, that generation at the edge of the grid, in either the industrial, the commercial, or the residential settings, is also partaking into that balance of the grid in really impacting, again, what I said earlier, power quality, modulation and harmonics, and the notion of that two-way flow or multi-flow of energy meets itself at multiple places, not just at the substation, but it meets at the line fuse or the feeder or the reclosure level or the transformer near to your house. And so the power systems need to be architected and thought differently. And so we are proponing at LTSCT a new set of reference designs that would help the OEMs, the original equipment manufacturers of all those devices in the grid, to basically create what we call solid state solutions that rely more on semiconductors and less on wires and magnetics. And so we need to shift to solid state solutions, leveraging semiconductors. And so we are building an entire product line for that. And we are currently recruiting partners that we want to build those systems with us. We're also envisioning an architecture for the utility that allows the utility to define this new state of paradigm where this new way bidirectional power flow enables consumers to become prosumers, meaning that they can actually not only consume energy and pay for it, but they can also, as they produce energy, they use for themselves, but they have excess capacity, they can also sell that energy back to the utility or perhaps directly on a peer-to-peer fashion to others on the grid, either their family members nearby or anybody they choose to. And so the importance of that new shifting is that you're moving away from inertia-based synchronization, which gives you anywhere from 5 to 10 seconds to make a decision. Seems like it's not a lot, but in grid time, 5 to 10 seconds is an eternity, and that's actually how the grid is managed today. 6 guys at a time, 8 hours at a time on every grid power station, and but so that 6 to 10 seconds is actually being impacted by these real-time control, real-time back and forth on the edge of the grid. There now needs to be inverter-based synchronization, meaning within a cycle or 2 cycle times, and that would be 1 divided by 50 or 1 divided by 60. So anywhere from 17 milliseconds to 20 milliseconds, depending on your geography. And so all of a sudden, the 10 seconds look like eternity compared to 20 milliseconds. And so the infrastructure to respond to that, and the frequency and the speed at which that happens, takes you away from electromechanical things and pushes you dramatically to semiconductor-based systems. And so in order to do that, you need real-time communications, which means you need either wire technology, fiber, or you need wireless technology, 5G or 6G or other point-to-point Ethernet technologies that allow you to touch all these devices and make sure that they stay healthy, they stay charged. The capability of what they're supposed to be doing and delivering is happening within the key performance indicators that you're tracking, right? And so that in itself creates an incredible new complexity that you're not just managing the power grid itself and the electrons flowing for electricity, but now you're managing a telecom infrastructure that is dealing with all the devices that are delivering the electrons back and forth, right? And then you need to make sure that all this is incredibly reliable, that it lasts a long time. Unlike the cell phone that you have in your pocket and the things that you buy for your house that usually tend to last 3 to 4 years at most. The grid is designed that every component of the grid lasts anywhere from 10 to 20, 30 years. So the type of reliability, the type of sophistication, the type of quality that is needed on the grid is very sophisticated. It's very, very difficult to achieve. So we have been, again, with partners, creating a new set of products, semiconductors, leveraging silicon carbide and gallium nitride and other wide bandgap materials, and new technologies from vertical power stacking to other things, system integration, that deliver next generation reliability, not only on the speed and the switching and the versatility of the voltage ranges and amperage ranges, but also on the temperature, and then more importantly, the ability for them to be programmable. And so as these resources, these devices, these components come together in harmony, sort of like a conductor talking to a symphony, you need all this orchestration being done, simultaneously. And the big thing where we're heading is that today the grid, the real-time grid today that exists, is only managing a few thousand things, maybe 100,000, 200,000 things real time on that grid. That is going to explode to tens of millions, hundreds of millions of things, which requires, again, more semiconductors, but also software to manage it. And obviously, the only way to control all this and build a self-healing grid is with artificial intelligence, which is at the core of the new generation semiconductors that we're building.
Wow. So I think this slide is a delicacy to all the innovators, irrespective of which domains they are working on within semiconductors or at a product level. You spoke about the decentralized architectures and distributed generation and storage, especially DC-DC, which I'm sure will generate enough curiosity. You spoke about the last bullet is very interesting, integration of diverse energy sources, from renewables to nuclear to other advanced futuristic technologies, which is amazing. That a grid is going to be a kind of a melting pot for different energy sources. And another key word that you used earlier was the consumers and the prosumers, which is really interesting. And
Mm-hmm.
the people who can not just consume but give it back to the
Mm-hmm.
grid. Amazing. And the real-time control systems, I'm sure they will have the latency and bandwidth related challenges that will advanced semiconductors like never before. But
Mm-hmm.
Andreas, all that is only going to be possible through something which is very special to all of us, which is the next generation semiconductors technologies. And that leads me to my next question, that how are the advancements in semiconductors technology that will make all that possible? Because otherwise, at least I don't see how it is possible. So please share your enlightening thoughts on that.
Well, the truth of the matter is that the grid is using, a design in an architecture that is very dated, and and um, and we're still primarily really living in the electromechanical world, where, believe it or not, I tell people the story that, I have multiple friends, and I've been in the energy industry now for 22 years. Um, I have multiple friends that started their career as a substation engineer. And a substation engineer, 30 years ago, it's somebody who graduated with great honors in electrical engineering, and they got hired as a started job as a substation engineer. And their job was to get to a substation with a key, open the door, walk in, sit on a table that had a red phone, and wait for the red phone to ring. And when the red phone rang, they talked to you and said, "Okay, Jimmy, you go and open the switch." So you would get up, hang up the phone, go and open the switch, which was basically this big lever, you know, and then you would have done your mission, come back to the phone and say, "Okay, I opened the switch," and that was it. That was the job. so so we have come a long ways from those days, but it's still, we're just starting, right? And we're just starting. We kind of take the world for granted, as many of us really don't understand the electric world and how electricity is created and delivered to you, and you kind of take it for granted when you flip the switch in your house. But the truth of the matter is that semiconductors and solid state devices can add great value, because, again, what's going to happen is we're moving from a, you know, somewhat, you know, slow, traditional one-way flow grid where not much is happening, to one where now at the edge of the grid with the solar panels and the Teslas and the gaming stations and all the fluctuation that is going on at the edge of the grid is transforming how the grid is behaving because of harmonics and modulation and power quality. And so you need new materials. You gotta go beyond silicon and really take advantage of things like silicon carbide or gallium nitrate or other wide band gap materials that really have 10 times, 20 times better energy efficiency. They have similarly better switching speeds, faster switching speeds that actually cover better range of voltage ranges from anywhere from 600 volts to 800 volts to 1.2 uh, kilovolts to 1.7 kilovolts, 3.3 kilovolts, 4.5 kilovolts, 6.5 kilovolts, 10 kilovolts, 20 kilovolts. And so all that is driving the need for new materials. And as you move away from the magnetics and the electromechanics devices components to solid state components, you're basically walking into the need for better semiconductors, better performance, very better efficiency. So with that kind of new semiconductors at the level of the transformers and all the components that move the power across, you would start to gain significant efficiencies. Today, for every dollar that you burn a fuel, either nuclear, coal, natural gas, for any dollar that you're burning to create a fuel, or for every dollar that you're using to transform energy, from photovoltaic or wind, in motion to electricity through the power lines, transmission and distribution, all the way to the final destination, your house, the building, the office. Every dollar that you're burning or spending on creating electrons reaches only 50 cents down the line, because there are so many losses and so many inefficiencies due to the electromagnetic and electromechanical nature of the grid today. So think about that for a moment. If the budget to make energy is $1 billion, you only get 500 million of delivered energy at the edge of the grid. So by switching to solid state components, by putting semiconductors everywhere and eliminating magnetics and electromechanical infrastructure, you gain a tremendous amount of efficiency. You reduce the losses of the grid, and you also allow for the control of the modulation, harmonics, and power quality that is being disruptive at the edge of the grid to many of the stakeholders that participate now and want better power quality.
Wow. I think this looks very fascinating for all semiconductors, power semiconductors engineers, that too many innovations and too many challenges are right ahead of everyone, and really make something for this domain as worth doing. And I think interesting point, Andres, that I believe is, this is such a niche area for every country in the world. Just case in point, somebody was narrating that in India context, the amount of power grids that will be designed in next 10 to 20 years will be, multiple times of the grids that are done in last 75 years since our independence. So that shows that the potential of what you're saying, both in terms of the disruption as well as in terms of the semiconductors impact that the world is going to watch. And I'm sure the same is the case everywhere in the world, where old grids are going to be redesigned. Amazing.
Absolutely. In fact, India itself is going roughly from 450 gigawatts today. They have approved, the government has approved a plan to stimulate the economy and the infrastructure and the ecosystem to build the grid in India up to 2,000 gigawatts by 2040. And so the grid took in India some 80 years to get to where it is. And now within 10 years or 15 years is going to quadruple in size, as it should be, right? Every citizen should have power. Every citizen should have water. And so, but the same is happening in the U.S. The U.S. is going from 1,100 gigawatts to 3,000 gigawatts. Europe is going from a similar number like the U.S. and China is going from 1,600 gigawatts to 4,000 gigawatts. Wow. So globally, energy is exploding because of electrification of vehicles, because of data centers, because what's going on at the edge of the grid, because everybody wants better security, better reliability. And manufacturing is moving from traditional humans doing everything in a factory to everything being 100% robotics, just like semiconductors have been for a long time. Now that robotics concept is coming across all industries globally, which means more electricity, more electricity, more electricity, more electricity.
And since this is all power semiconductors, maybe this opportunity for all our audience who are watching us and hearing us. From a talent perspective, this area is going to boom, just like Andres explained. If the demand is going to be so much and if the supply is so small, there will be so much of demand for those talented engineers who are going to design these different newer geometries in silicon carbide and GaN in days and years to come. I think it is a dream run for any semiconductor engineer in this space.
Absolutely. Yeah, I remember when I had worked in Seattle for Microsoft and moved to Silicon Valley and then moved to Boston. And I remember when I joined Austin Energy in 2003, a lot of my friends from Silicon Valley called me and said, "What have you done? You're destroying your career. Why are you joining an electric utility?" And I told them, "Look, you have to be patient. and watch what I'm working on, and in a couple of years, it'll all make sense, right? And so I came up with the concept of the smart grid in March of 2004, built the first smart grid in Austin. Since then, I've designed the grid in Dubai, Turkey, Abu Dhabi, Brazil, in 17 states out of the 50 in the US. And it's really, now everybody talks about smart grid this, smart grid that. And it kind of, it gives me a tickle because I came up with the word, I came up with the concept, and now we're living it. But we're still just starting. I mean, this is just starting, because it's really the digitalization of the electric industry on steroids. And so that's what the exciting part of being here, Sanjay, with you and the team, because I have all these dreams of that grid of the future after having designed the grid in so many places and what it should look like. And now we're going to sit down and start building it and partnering with the right people to deliver it. So I'm very excited about that.
Amazing. This is really exciting. Thanks for really getting deeper into this aspect, and lovely. Now, my next question is, we all talk about that hardware is not as hard it seems because there is a software on top of that. So my next question is related to while on other products which are typically not in power semiconductors, in compute, for example, we always kind of realize that yes, application, software, ecosystem is an important part. And when it comes to energy and grid, right, the first impression is probably software has no play in that. But the way you have explained the kind of real-time requirement, the kind of faster switching speeds, the kind of the multi energy sources need to get integrated, and the way you need to differentiate between consumer and prosumers, all that require a very high intelligence and AI capabilities and automation. So my next question that is, how do you feel that on the software front, the increasingly complex grids will be managed using what all attributes and what all features, which probably are not very clearly visible to the common man in the industry, and how software will be the differentiator in this very complex hardware.
Yeah. So remember that you mentioned my books, and there's a book that everybody should read called The Advanced Smart Grid that I wrote first edition in 2011, and the second edition in 2015. And I'm actually planning to add a semiconductor and a cybersecurity chapter to that book during the journey here, or after the journey here. We'll figure it out the time for that. But electric utilities use couple main software tools to manage what they do today. They use SCADA, supervisor control and data acquisition solutions, to manage all this programmable logic controllers or IEDs or anything that touches the grid today. And then in order to balance the grid, they use something called energy management systems. Now, as the utilities have evolved, they have traditionally, they evolved from, having the power plants being managed by their distributed control system, and in the SCADA and the EMS to really move the electrons and track the movement of the electrons through the transmission line to the substation. But then traditionally, there was nothing after that. Now, over time, the utility has, sort of created point solutions to say manage meters. So there's traditionally there were drive-by meters, and eventually there were, wireless meters that could be managed through AMR, automated meter reading, which use all kinds of different wireless technologies, point-to-point, 900 megahertz unlicensed spectrum, or a power line carrier using the wires of the utility itself. And then eventually you move to a broadband concept behind that. So there are new standards like Wi-SUN, or you can use, obviously 5G, 6G, or Wi-Fi for broadband capability, closer to real-time controls on those devices. But then as you decided to instrument the edge of the grid, putting gateways for distribution automation, or managing your reclosures or feeders or line fuses or what have you at the edge of the grid, your transformers. Now all of a sudden and then sensors on the grid, those volt bar control sensor that you can put on the grid and buy from anybody. Then all of a sudden you have this, point to point solutions that have been built. And then, the latest thing that most utilities are, working on, which I had the pleasure of working with GE in 2006 and designing the very first distribution management system in the world, and deployed it at Austin Energy. Now Austin Energy is on its fifth distribution management system since then. But I deployed two of them. And it's basically the notion of a SCADA and an EMS on steroids at the edge of the grid, managing all these devices real time, and maintaining that grid reliability in the frequency at either 50 hertz or 60 hertz. And so what needs to happen then is, as the edge of the grid has evolved as well, and you have a battery management system managing your battery on the edge of the grid, or you have an EV management system managing the electric vehicle that can maybe do, charging the grid, vehicle to grid, as well as taking energy from the grid itself. All of a sudden you have these systems that are called now distributed energy resource management systems, a term that I coined in 2015. And these DERs have their own system, and they need to be integrated to the DMS or the ADMS, Advanced Distribution Management System. So software and programmability, Sanjay, as you know from the computer world and the other markets you've worked on forever, are super important to the longevity and the actual delivery of the quality and the experience of the assets that you're delivering to do automation. So the grid needs to become not only programmable, but it needs to become self-healing driven, so that the AI talking to the microprocessors, the controllers, the BMUs, the BCMUs, the inverters, the semiconductors inside those inverters, right? So we have this amazing product lineup that I would like to talk to you guys about, and hopefully we can have more discussions in the future. So be in the lookout for our PowerSync product line, our PowerGain product line, our Power Store product line, our Power Center product line, and our Power Edge product line. And these are product lines designed for the energy storage space, the devices at the edge of the grid, data centers in particular, and then all the power components, the power modules, and the power delivery that is needed through power modules for different elements of the grid. And so software management and software control and software programmability, and then AI itself are fundamental. And obviously, all this, as you open it up with software, brings the notion and the imperative need of cybersecurity. So in the power world, as I energy from and managed over 2 million devices real time for the utility from 40,000 when I joined. Cybersecurity trumps everything. In the power world, having an outage is not acceptable. Having an interruption is not acceptable. Having non-reliability is not acceptable. So in a world of programming and microprocessors and memory and data, cybersecurity becomes paramount to where the grid of the future is. So we are planning with your team all these ideas of embedding cybersecurity not only in the software solutions that will accompany and help the design of new systems using our semiconductors. Again, we just made the semiconductors and the software tool to design the new systems, but we're very excited because we're also looking at embedding some of that cybersecurity or physical security elements into our own semiconductors. So we have already submitted several patents on that. And we're looking at really reinventing and reimagining how the grid of the future functions by leveraging software.
Amazing. I think it forces me to think that possibly the future of energy generation and smart grids is one area which is driving two extremes or pushing the boundaries, one on semiconductors technology, pure hardware going to very
Mm-hmm.
high voltages, as you explained, into
Mm-hmm.
multi-thousand volts, versus say point millivolt of operation at a transistor level. And the other hand, the software is going to be the key for all the reasons you just mentioned. And
Mm-hmm.
one thing that catches attention is, of course, cyber security, because all the Hollywood movies we see, where some of the sci-fi fiction and some of the bad people try to take control of the whole city and the country,
Mm-hmm.
the power grids. So it is both a joke as well as a serious question. Do you see that this could be a real differentiator? And it's great that at L&D Semiconductors we are putting it right at the foundation for our design efforts and all the patents that are being filed on that. But do you really see that in future, if somebody does not take care of cybersecurity and software as a serious affair, you are actually having a big risk that can be opened up to the whole society?
Absolutely, absolutely, and I think that is the biggest imperative of the transformation and how the transformation sort of needs to happen. Is almost the same concept, as a metaphor on the concern of how AI develops and will AI be detrimental to humanity. So the grid of the future requires to be real time, two-way power flow, programmable, self-healing, which means software. And if you don't do it right and don't design it right, and don't think about all the use cases and all the components of the use cases tightly integrated from the bottom up in terms of how the system boots up, how the hardware is totally certified, and how the software is totally certified and embedded perhaps on the hardware itself. If that is not done properly, then you're really, creating a disaster waiting to happen. So
Absolutely.
that's why we're excited about our thinking about how we are planning on building these next generation systems, on how we are reimagining through our reference designs, both for the original equipment manufacturers and the systems that they make and the utilities themselves, leveraging our semiconductor technology and our software for the development of those new systems and those new architectures. That's going to be one of the key things about joining our energy partner program as an OEM or as a grid operator, to really learn and understand these next generation systems that we're building. We have been hiring a phenomenal team, and both your shop and my shop, and I'm very excited about what we're discussing with new partners. Currently, they have understood my vision of what this two-way power flow, two-way data flow, real-time control grid of the future looks like, and how we can, with the new reference designs and our new semiconductors, build something that is rock solid and can scale to infinity.
Wonderful, wonderful. And with my R&D hat, maybe use the opportunity to call out for all talented software engineers as well as hardware engineers to come and join this mission, which will be a game changer for society and the world in general. So great. Now, with that, all the positives and all the opportunities that we have gone through, right? It obviously leads us to think that, okay, there has to be some blind spots, there has to be some challenges, and so that we
Hmm.
are ahead of time, ready for those. And that is where my next question is, what are the key challenges that we need to overcome, and what are the biggest opportunities once we move over those challenges? Uh, so please throw some light on
Yeah,
that.
yeah. So I mean, the biggest challenge on anything new is yourself, right? Not wanting to change, being comfortable with where you are. So, a large industry driven by monopolies, utilities are monopolies, right? For in most countries, in most segments. So that the notion of not wanting to change, of wanting to take it easy, wanting to go slow, is definitely a challenge, and that also creates a regulatory challenge, and obviously, part of the part of the challenge of not wanting to change and the new regulations needed to enable or improve things. So, for example, go look in the U.S. FERC 2222, the Federal Energy Regulatory Commission Order 2222 was created in 2017, and it was designed to basically enable this two-way power flow, energy storage, aggregation at the edge of the grid to be part of the whole grid system. And that order is yet to be implemented because the regulators and the ecosystem that works with the regulators is afraid of that order and is sort of dragging their feet to, can we really allow this aggregation of energy storage at the edge of the grid done by whoever? It could be Google, Microsoft, Amazon, Tesla, anybody could do it. Basically take all the EVs or the energy storage at the edge of the grid and then make them look from being disaggregated physically to being one virtually, like a hard drive virtually, right? And now all of a sudden you can play in the edge on the power grid as one player, having all the capabilities of the separated, distributed little assets that show as one virtual single large asset, which is the magic of software, right? And so we need to, the utility industry is waiting for someone to lead the way on what does this new architecture look like? What are these new sustainable, resilient energy systems look like? And then obviously, how does this whole thing get paid, or what is the cost? So what is the cost of building the dream of this new grid, geography by geography, trillions of dollars? Where does that money come from? How does it happen? Who pays for it? So that goal goes back to, unfortunately, politics, and goes back to regulatory decisions, right? On how this all happens, how the prosumer, the producer and consumer becoming one person. This is the prosumer term was invented by Alvin Toffler in the third wave in the 70s, when he came out with his book called The Third Wave, and basically refers to the notion in the power industry that I consume electricity, but I also sell electricity on the grid. And today, in most geographies, if you're allowed to do that, meaning sell your excess capacity back to the grid, you are buying that energy from the utility at retail price, but they buy it from you at wholesale price, which is really a robbery when you think about it. But they're a monopoly, and eventually in some geographies, the notion of me being able to sell my excess power to my cousin or to give it away for free to my mom should be allowed. But today is not allowed in most geographies. Only a few places allow this today. So the notion of changing the business model and the relationship with the consumer and creating new energy markets and how energy will flow, it's almost like allowing the decoupling of the physical commodity from the virtualization or the transaction. And today, the commodity is pretty much tied to the transaction because it's delivered through a monopoly, and that needs to change, and that will enable new things, right? And it'll accelerate the transition towards clean new futures, because in the end, energy storage is the holy grail. If you have the opportunity to work in energy storage, and by the way, we are building a phenomenal BESS and BMS solution right now. If you are interested in that, you should come and work for us. But we are, really reimagining all that. So while there are challenges, and obviously we need, new evolution on the wide bandgap materials, we need, to go beyond gallium nitride to maybe gallium oxide or diamond or some other materials that need to come, and how do we use binding materials like sapphire or aluminum nitrate or other things, right? So it's almost like Sanjay, to me, it's almost like it's a toy store. I mean, it's just, there's so many things that need to be figured out, and it's so exciting. It makes me come back to my first thinkings of when I took circuits or dynamics, and my brain was exploding with all this thoughts about what could it be and how would it be, and as you learn and learn. And so we are, by doing this transformation, we're unraveling how the grid is going to be reimagined and transformed, and how these components get to be integrated, and how we migrate from the current state of the grid, which doesn't have to be sophisticated for many in some cases, to a grid that needs to be highly sophisticated because everybody has a Tesla and a Powerwall and solar panels in their house and what have you. But it's obviously a journey. The thing that I remind everybody is that a major transformation, and I'll do a quick plug here. I had the pleasure of working on Windows for Microsoft. Did the first 4 versions of Windows from 86 through 89, and it when I left Microsoft, I thought that we were done, had conquered the world. We were a $1 billion company from zero, and clearly Microsoft did way better than anybody thought possible. Obviously, for the great leadership of Bill Gates and others in the team, but it usually takes 20 years from a major transformation to happen. So while I coined the term smart grid in 2004 and built the first smart grid in Austin Energy by 2009, we're still in the first 10, 15 years of that understanding of, and so the next 20 or 40 years, because electricity is so massive globally, so if you come to this space, if you work in this space, you got the next 30, 40 years to have fun building all kinds of things. And perhaps the biggest challenge will be, how the, cybersecurity gets implemented and to deliver what I call a self-healing grid with AI, where the robots are running everything smoothly and they're turning on and off and connected devices and settling pricing, and everything is beautifully managed. Sort of like how the internet happens, and we kind of take it for granted.
Amazing. I think the kind of opportunities and the kind of technological challenges, both hardware and software, the kind of business models where you can feed the grid and generate your own energy, the way you can have multiple energy sources feed into the grid, the way you can have multiple new technologies which will be driving it from silicon carbide to GaN. I think this is truly like a kid in a candy store, a feeling, right? So the excitement is really that whosoever wants to have next 30, 40 years of fun, this is the area to be in. And I'm so happy that at L&T Semiconductors, we are privileged to be driving it right from the core for the overall the grid architecture with visionary leaders like you, the entire development right from the bottom. I think it is happening in our company at R&D level. So sky's the limit for us to achieve. And that excitement asked me to give you a final word on simple takeaway. What would be your takeaway in terms of these are the top 3 or 4 areas to ponder when you go into the space?
Yeah. Well, given the growth that we outlined that is happening in Texas, the U.S., India, Europe, China, more electricity for all kinds of needs, the next generation power grid is essential. It needs to be built. It needs to be designed. Right? We should not be sitting here and being content with the current grid and the lack of capabilities that it has. So what we're envisioning with our reference designs for both grid operators and OEMs is paramount. It's part of our energy partner program. Is going to leverage all the semiconductors that we are planning in our own, solutions, from the PowerSiC Plus, PowerGain Plus, PowerStore Plus, PowerCenter Plus, and PowerEdge Plus product lines for the edge of the grid, data centers, energy storage, and power in general, for all kinds of components, inverters, converters, so on. And so, new materials are needed. The two-way power flow is critical. The programmability, the AI element on it is super critical. And then the biggest thing about it, Sanjay, is the collaboration. We, even though, some folks may seem like they're competitors or they should be competitors, the truth of the matter is that when you are tripling or quadrupling the market you're in, there is room for everybody. There's space for everybody. And so we're excited about building a incredible tent of collaboration and partnering with everybody in the ecosystem. So from the largest, most successful GPU, CPU companies to the largest and most successful silicon carbide, gallium nitride silicon companies to small startups. We are currently collaborating and looking to talk to everybody, being a fabless company, partnering with all kinds of foundry companies and power module integration companies and all kinds of new technologies that are being dreamed up. So our CTO office is very on top of all these things and building a phenomenal set of roadmaps for us to explore on the product side. And your team is fabulous, and we continue to hire rock stars from all over, from Australia, Europe, and it's just, I'm so excited about working with you and what's going to happen in the next 2 to 3 years, let alone the next 5 and 10.
Great. Thank you so much, Andreas, for such a lightning excitement that you have created to everyone. At least I'm feeling very excited to jump and start working on my next project tits and bits to make it happen. So we have a lot of audience, and I think we would like to go for audience Q&A. So I'm sure they will have plenty of questions, and I just repeat that if you have a question, you can write in a Q&A box onto the Teams window, and we'd love to take it, what is in your mind. Okay, so we have some questions. Let me start with the first one that I see on my window. So this question is from Jyoti Kaushik, and his question is how semiconductor and next gen grid can help reduce transmission losses.
Yeah, like I said earlier, for every dollar that you use to create an electron, you end up delivering only 50 cents at the edge of the grid. There are, anywhere from 3 to 5% losses due to the notion of electromagnetics and the distances of the grid. So in many ways, alternating current grids were the way to create electricity and deliver it to the masses in a very cheap fashion, thanks to Tesla's design. But we all know now that the real better architecture is a DC to DC architecture, where the generation of the electricity is somewhat co-located with the demand of the electricity. So in many ways, Edison lost that intellectual battle versus Tesla, but I think in the end he gets vindicated as we move to a DC to DC world where the generation happens everywhere. So every building should be its own power plant. Every school, every house, every factory should be its own power plant. And we are starting to see it now with the thermal solar wrapping buildings and microwind generation and all kinds of other motion and vibration generation technologies and techniques. So transmission will always be there because you need to move the generation from central utility scale to melt steel or things like that, right? So you couldn't walk away from that anytime soon, and certainly not in our lifetime. But clearly the edge of the grid is going to play a bigger role, just like personal computers and the cell phone sort of now dominate and we kind of take it for granted. Similarly, every building in the world will become its own power plant. So that will sort of, transform the way the grid is done. But if you, in the current grid, move away from electromagnetic systems and move into solid state transformers, which require semiconductors and so on, then the energy efficiency and the losses on the system will get minimized by 30, 40, 50% over time. So again, every dollar that you burn to build an electron, you get 50 cents at the edge. So maybe instead of getting only 50 cents, you'll get 80 cents. And that in absolute dollars globally is a gigantic amount.
Great. We have another question. By the way, I repeat, the chat box is frozen, but there's a Q&A box right next to that. You can write your questions there because a lot of people have raised your hands. It will be great if you can write your questions. I don't know if the line can get open for audience, but while you're writing the question, I will read the next question from Vipin. What is the potential size of the semiconductors opportunity in this power grid design? I believe the question is in terms of the dollar value of the opportunity and what percentage market we are targeting from L&T Semiconductor.
Yeah, I mean the numbers today are in the billions. It's a small number still compared to where it will be as the grids grow, 4 times over the next 10, 15 years. But eventually, the opportunity of just semiconductors on the power grid will be, probably close to 500 million, or something like that. So, we have serviceable, addressable markets today that we are looking at. There are almost $10 billion by segment. So data centers, energy storage, high power modules for wind, solar, and then devices at the edge of the grid, integrated units, meters, things like that. So when you look at all that, today for us is roughly $10 billion of addressable market that we're focused on. The larger, power semiconductor business today, roughly industry-wide, is about 40 billion, but that's going to grow 10x in the next 15 years.
Wow, that's great. That's great. There is another question that I would like to ask on behalf of, I'm sure many people, that is very vibrantly coming to my mind, is just like we have automotive standards for software for, automobile market. Do you see that for energy, considering the cybersecurity and real-time control is going to be so crucial for its success? There could be a complete dedicated operating system from software standpoint, which targets energy segment, like Energy OS.
Yeah. So the answer to that is that the industry is already very well standardized, right? There are multiple standards for power, for telecom, for cybersecurity. There are standards for inverters. The IEEE, the IEC, ANSI. There are multiple organizations globally that basically provide the standards for how all these power devices behave and are built. You got obviously UL and CE for the consumer interaction with those devices. You have, obviously all kinds of capabilities, not only on power and standards, but on telecommunication. And then, you have multiple organizations, IEC being one. The Department of Commerce owns something called the National Institute for Standards and Technologies, NIST, in the US. And NIST has a standard that was created from 2009 when I participated, one of 7 directors nationwide that collaborated with 1,000 engineers to create the standards for NIST. And I was a board member of this smart grid interoperability panel back then. So there's a whole grid standard that exists today from the U.S. government, Department of Commerce, through NIST, the National Institute for Standards and Technologies. And then there is also cybersecurity standard and framework that they have created. So obviously, these are sort of best practices that have been accumulated over time. Then you have within the U.S. market, for example, the Federal Energy Regulatory Commission, which mandated the North America Energy Corporation, NERC. So FERC told NERC to basically create these cybersecurity standards. So there's a list of best practices, cybersecurity standards for the industry. So we're, again, just at the beginning of where this is going to go. It's going to explode in many ways, like we take it for granted in the retail industry or the airline industry or the financial industry or the medical industry, where there's a gazillion standards for all kinds of reasons, and those industries are a lot more digitized and being, dependent and reliable on software programming, and it's vulnerable to cybersecurity. The same thing is going to happen in the energy space.
Okay, great. And I'm pretty sure that you talked about so many compliances that will be required. So just like I'm relating, automotive has functional safety ISO 26262. Similarly, as we move forward and evolve this very interesting area, there will be dedicated standards that will evolve. And I'm glad that with your leadership right at the top, we are going to drive this energy products compliant to the best in class in the world, and really make them really expand to the reach the globe.
As you know very well, one of the beauties of building a new company from scratch is you get to build it like you want to. So I'm happy to share with the audience, and hopefully many of the audience are our own people listening in, that we have a great quality team. Your team is kind of driving and participating in a huge way on how we're going to become ISO certified in multiple levels. And obviously we're building also all this next generation best in class processes and best practices. So I'm very excited about how not only are we participating in the industry, but how we are actually helping the industry improve overall, and we can be a poster child for how other companies get into the journey of building next generation systems.
Great. We have time for probably one last question. We have Mr. Sunil Lekhwani. He's from Schneider Electric. If you can kindly write your question on the Q&A box, that will be great. We won't be able to open the line at this point. If you can do that, that will be really awesome. And while Sunilji may be typing it, all I can say that Andres, through this last hour and 15 minutes of talk, the aspects that are being touched, from systems to hardware to software to compliances, they are really mind-boggling. And I'm sure that while we are leading the way, as you rightly said, there will be a lot of partners, a lot of collaborators that will come along, and together we are going to scale up this huge opportunity, not just lying in front of one country, but literally the entire globe. So it's really a lifetime opportunity, as it seems like.
Yeah, I would encourage everybody to circle back with us. We are launching our Energy Partner Program. There are multiple levels of that program to participate with us in getting access to our reference designs for both systems and power grid players. You'll also get access to our engineers. You'll participate in 2 annual conferences that we're creating for developers. You're going to be able to also participate in the different working groups for the different 5 product lines. So as I remind you, it's the Power SIC product line, the Power Gang, the Power Store, Power Center, and Power Edge. And then you will be also getting access to our best practices and capabilities and laboratories for testing, modeling, and simulation. And we are building world-class facilities in Bangalore, in Munich, and Tokyo, and Austin, Texas. So we are, just in the early stages of all this, but it's all coming pretty fast, and we are growing pretty fast. And the interest in the industry is pretty high on our technology and our thinking. And you continue to hire great people, and we are very excited about what this all can bring. So
on this, we have one last question as a special request, and then we will have to wind up. So this is from Mr. Satvik, and I read, what would be your advice for young entrepreneurs who are passionate about collaboration and eager to contribute to the ongoing technology revolution, especially in identifying and solving pressing problem statements in this area.
Well, I think our marketing people are going to be doing a very powerful job of outreaching. I know that you created this series session, and I'm delighted that I get to be the first one to kick it off. But I think that this series session will continue, and I know that the marketing team is looking at building different ways through social media in our upcoming conferences in the future on how the world can interact with us, be it students or startups or the media or the ecosystem at large that exists today. So now, if I were to extrapolate the question about who knew 30 years ago that electricity or energy was going to be such an exciting place? Most people that went to study computer, electrical engineering, studied computer engineering, which I did, but very few people paid attention to the power side of things. So I would say, get involved in power, get involved in materials, learn about AI and how it all comes together and changes the world. We're in the middle of it. So, I know that we're hiring a bunch of people. So get a job at LTSCT, is what I would say.
Great. In many ways, the punchline for this series first talk, thanks to you, Andreas, is powering the future of energy, right? So this is the real power. And I'm very confident that with L&T Semiconductors leading along with a lot of partners and stakeholders, we will be really making a game-changing impact to the world in this area. So with that, I would say the last page on the slide has the contact email ID in case anyone is interested to talk further. This was only a series to, you can say, scratch the surface, but there's a lot beneath it. So please feel free to reach out to our Connect ID or any one of us, and we'll be very happy to take it further in terms of the next collaboration opportunities. And I would also like to take the opportunity to thank Andres, you, the entire organizing team for this series with Alejandro and his entire global team for a wonderful job. And I'm sure this will be one of its kind to promote the next generation futuristic technologies and how L&T is taking a lead on that. So with that, thank you to everyone. Thank you, Andres.
Thank
And
you.
thank you to all
Thank
our
you.
listeners for your time, and looking forward to have many more engagements like that. Thank you, everyone.
Thank you. Thank you, everybody.